Okay, so now we're going to start a new topic, which is basically the general area of adaptive filtering. And much of what we've talked about to this point is basically systems of the form, digital systems like I've got an input, I've got a filter, and I've got an output. And this H is assumed to be an LTI system. And for example, this H could be an FIR filter with N taps. And so we just spent the past few lectures talking about ways of designing that LTI system. If I specify a desired frequency response and I specify the number of taps or the constraints that I need, and I specify the metric by which I judge how good a filter is, we kind of now understand more or less how to design a good filter, right? And so, for example, maybe I've got a system where I've got some sort of noise, and that noise maybe is got a frequency response that is concentrated in some particular frequency band. And so maybe what I might want to do is design a corresponding filter that will basically pass everything and then notch out the places where this noise is, right? And so this would be kind of like a band stop filter, and we could design that. So yes, we know how to do that, but the problem is that in most situations we may not exactly know, for example, exactly where is this noise in the frequency band. We may instead have a probabilistic description, a probability distribution of where the noise is, and we want to design a filter that is optimal in some sense in removing the noise in some sort of an expected value kind of way. And it's possible that this noise may move back and forth in the frequency spectrum over time. So this filter we may want to change, right? And so in this kind of case, we don't want to use a hardwired filter H. We want one that adapts to what's happening in the input and what's happening in the noise at any given time. And so in the kind of case where we've got this FIR filter with N taps, that's like saying that I want to be constantly updating these N taps at every point in time to do as well as possible. So it's like a filter design problem where the coefficients are constantly being updated. And that's called an adaptive filter, okay? And there are lots of really interesting considerations for designing adaptive filters, unfortunately many of which we won't be able to get into too much, but just here are some issues like, how fast does the filter converge? How well does it track things like, where the noise is? How robust is it to noise and errors? How complex is it in terms of, details of filter design? So these are all like really interesting issues. And so we're not going to get into these too much, but just to think about, okay? So at this point, what we need to do is combine all of the kind of signal processing that we've done so far with concepts from probability theory. And for those of you that are more advanced, things like stochastic signals and systems. And so now we think about this input signal as stochastic, which basically means that it's random. And so instead of assuming that we know the exact value of x of n at any given time, we basically have a CDF or a PDF on x of n. So we describe each value of x of n with a, for example, a cumulative distribution function, the probability that xn is greater than some value t is equal to an integral like this, where I have some probability density function, right? That's like saying I have some PDF that, integrates to 1, and if I tell you that I want to know what is the probability that x of n is less than this, I integrate that PDF up to here, which is the same thing as a CDF, right? So this is like a, PDF that depends on n, the index of the signal, and this is like the CDF for n, right? And so now we have to think about all these tools that we developed from probability theory, right? So for example, I have a mean that depends on n, which is the expected value of this x of n, and we know that the way I compute that mean is by doing this integral, right? So this is just the formula for the expected value of something, right? And in the same way, just like we talk about expected values, we talk about covariances, right? So when I've got a single random variable, I talk about its mean and its variance. When I've got multiple random variables, I talk about their variance like this. So this is called the autocovariance. So I'd have something like, you know, how are the variables at time n and time n minus k related? That's given by the expected value of this guy times the expected value of this guy. And I'm just going to assume in this lecture that everything is real, okay? In general, the proper way of defining the autocovariance in the complex world is that I have to put a covariant, I have to put a conjugate on one of these, right? So this is called the autocovariance, or sometimes just called the covariance. Auto because I'm looking at the signal with itself. And then there's something that is related to that called the autocorrelation. So I'm going to denote that throughout this lecture by R. That's basically like the expected value of this, but without taking off the mean first. This is the autocorrelation. And this is going to be a super important quantity going forward, okay? Okay, so we know that the mean and the covariance, or the mean and the correlation, are basically, you know, a partial description of understanding the randomness of a signal, right? And that description, just with the mu and the r, is often quite useful, okay? And one of the key assumptions we're going to make here is that a stochastic process, which is just like this x, is stationary if the statistical properties are time invariant. And what that means is that basically, you know, those are really easy to analyze. For a stationary process, that means that the mean, for example, is always the same number, regardless of n. And the same way, the covariance, the covariance between a signal at two different points in time would be the same if I shifted those points in time by m. So all that matters is how far apart are these two numbers. And that way I can define basically a covariance as a function of this k. And sometimes this k is called the lag, right? So that means that if I look at the distance between, you know, these two numbers, I have a single number that defines the covariance. And in the same way, or autocorrelation, in the same way the autocorrelation is similarly just a function of k. So basically, you know, only depends on the difference in time, not the actual time that I look at it. And so, you know, this is kind of like a, you know, generalization of what we mean by time invariance, right? So just to be careful, so stationary is a much broader condition than this. So certainly if the process is stationary, these things are true. These things can be true. That's not sufficient for the process to be stationary. But these two conditions in particular, so let me just say that a process is what's called wide sense stationary, which you sometimes see abbreviated as WSS, if basically the second order things are true. If this is true and this is true, right? So a process can be wide sense stationary, but not fully stationary, but this is usually good for us. And so we can show that a wide sense stationary process satisfies the expected value of the sum of squares is less than infinity, right? And so this is generally true for most of the signals that we care about, right? We don't want to have some crazy signals that spike off into infinity. And so this is usually true, which means for our signals of interest, this is also usually true. Okay. So I should be clear. A stationary process is wide sense stationary if these things are true. Okay. So let's take a closer look at this correlation matrix. And what I mean by that is, let's suppose I have a vector that contains my current value of x and m minus 1 previous values of x, right? So this is a vector, and this vector is going to be m by 1, right? And now I can form a matrix, an m by m matrix, such that R is the expected value of this vector times this vector transpose, right? Again, since this is m by 1, this is 1 by m, that means this is going to be an m by m matrix. And the kind of ijth entry of that matrix is the expected value of x of j times the expected value of x of I, which is just what I defined as the autocorrelation of the difference between these numbers. And so that means that this R matrix has this kind of special structure that when the entries are the same, I have basically 0 lag. And these are just basically the variances at each point in time. And then along the diagonals, these guys are separated by 1, so I have 1 along this diagonal, and these guys are also separated by 1, so I have 1 along this diagonal. These guys are separated by m minus 1, and these guys are separated by m minus 1. So basically this is a matrix that has all the diagonals are the same. And so you can see that this matrix has some properties. It's symmetric. It has equal diagonals. And this has a special name called toplets. Okay, so a toplets matrix is one that has equal diagonals, and there's a Matlab command in toplets. There's a Matlab command called toplets that makes it easy to make such matrices, and it's what's called non-negative definite, which means that for any matrix or for any vector, x transpose Rx is greater than or equal to 0. Okay. So this autocorrelation matrix is going to play a big role in what we're going to talk about next whenever we talk about signals that are random. Okay, and so there are a couple of special, special models for stochastic signals. And, by what I mean by a model is basically it's kind of like a hypothesis for how is that signal generated or how is the data distributed. And so usually these models have parameters. So kind of what we're talking about today is, parametric models. And what we're going to talk about basically are called moving average, MA, autoregressive, AR, and then basically the combination of these, which is ARMA. And so I'm going to talk about all three of these with the note that, most of the time, or a lot of the time in signal processing, we look at autoregressive processes, and I'm going to talk about that in a second. So, for example, or noise, right? Noise is a good common model too. So let's talk about that first. So white Gaussian noise is something that you're probably familiar with from probability theory. What that says is that my signal value has a PDF that's given by this guy. And so basically white means that mu equals 0, right? So this is particularly easy. And so that means that the expected value of this noise is 0, and the expected value of the noise times some other value of the noise is going to be basically some sigma squared when k is equal to 0, right? Because when k is equal to 0, that's just like looking at the variance of the process. And when k is not equal to 0, I assume that things are, independent and uncorrelated, which means that one value of the noise doesn't have anything to do with the other value of the noise at a different thing. And so a different way of writing this would be sigma squared times a chronic root delta for, when n is equal to k, right? Okay, so let's talk about these signal models. So moving average model. Sometimes called or often called MA, basically says that the signal is generated by a combination of, basically a linear combination of noise values. BK, Bn minus K, right? So where these, BIs are constants, and this Vn is a white Gaussian noise process, just like we talked about in the last slide. And so this is basically like saying what I'm doing is, filtering white noise with an FIR filter, where the coefficients are given by the B's, right? So, I could write this in a different way just by saying this is like convolving I take the corresponding value of the filter and I multiply it by the corresponding point of the noise, right? So it's just like saying I'm convolving the filter with the noise, okay? Okay, so, that's kind of maybe not that intuitive, but you can kind of show that this is basically like a smoother in general, right? So, depending on how I select these things, it's like I can make a low-pass filter version of the noise or a high-pass filter version of the noise. It's kind of more common to think about an autoregressive model. So that's called AR. And so the reason this is more intuitive is, in this case, what I'm saying is that my xn is basically equal to a bunch of previous combinations of the signal plus some noise, right? So it's like saying that, my current value of the signal is some linear combination of the previous values plus some error term, right? And that error term, again, is assumed to be Gaussian. So again, here, these AI are constants, and the Vn is, white Gaussian noise. Right? And so, since the current value of x depends on previous values of x, it's regressing on itself by this a. And so, a different way of thinking about this is that, if I let a0 equal 1, that's like saying that the noise is the convolution of the filter with the signal. So this is basically like an IIR filter, right? Applied to noise. Right? And so, this is a little more intuitive in the real world because it's like saying that, in general, I expect that the current value of the signal is related to the previous values of the signal, offset by a little bit of error in that estimate. And so the ARMA model is basically a combination of both of these things. That's like saying that in general, we have the ARMA model, and that says that I have on the left-hand side the combination of a bunch of values of x. I guess I said m. And on the right-hand side, I have the combination of a bunch of values of noise. I guess I said this was k. And again, now you can see this looks a lot like basically the kind of filters we were talking about before, right? Because if I wanted to look at the transfer function of the system, it would be like the z transform of this over the z transform of this applied to input that was noise, right? So basically, I apply to noise process. And so, in general, AR processes are widely used, and if you want, you can also include the MA part that basically says that instead of operating directly on noise, I could operate on smoothed noise, for example, if I wanted to get a smoother process. And so let's talk about just the AR process. Okay, so let's assume that I don't have this part here, and I only am looking at basically the assumption that I'm related to my previous values plus a little bit of noise. Okay, and so what I want to talk about is how to estimate the parameters of an AR process. Right, so what would we need to know? We would need to know, these m numbers and the variance of the noise, right? So there are m plus 1 things to figure out, okay? And, it's also possible that we don't know what m should be. So also the order of the model m, right? And so, again, the way to think about this is that we look at the input signals that we get and we try and figure out, are these input signals well modeled by an MA process or an AR process? And if it's well modeled by an AR process, how do we know how many previous values we should look at and what the noise variance is and what the parameters that control the combination are, right? So luckily, there's a very nice procedure for doing this estimation process, and that's called the Yule-Walker equations. So and again, this is basically a straightforward application of probability. So let's take a look at the problem that we have. Okay, so here's our assumption. Now I'm going to multiply through by a given lag. where I get to choose this L. And now I'm going to take the expected value of both sides, right? So the expected value of both sides. And now you can see that I'm going to get quantities that are related to the autocorrelation of the sequence, right? Because the autocorrelation of this, or the expected value of this, is just what I defined as R of L, right? Because these guys differ by L units. I guess maybe I should say this is like R of L, like this. And then these guys differ by the difference between these things, which is R of L minus 1. And then these guys differ by R of L minus M. And then what is the expected value over here? Well, let's think about this for a second. So if L is greater than 0, let's say, well, that's like saying that here I want to know what is the expected value of the current value of the noise and previous values of the input. And so here, all this stuff happens before this noise term is generated, and I know that the noise is independent of previous values here. And so basically, this guy is going to be 0, right? So that means that on this side, the expected value is 0. And let's think about what would happen then if I'm going to decide on, again, this L was arbitrary, right? So what I'm going to do is now generate this system of equations for L equals 1 to M, right? So all I'm doing is I'm allowed to choose what is my lag, and so since I have M unknowns, A1 through AM, I'm going to make M equations so I can get a square matrix, right? So that means that, for example, when L equals 1, let's just take a look at what we get here. So that's like saying that for L equals 1, what does the system give me? R of 1. Actually, I'm going to write this again just to be really explicit. Right, so L equals 1 means that I have R of 1 plus A1 R of 1 minus 1 is 0 plus A2 R of, what is R of 1 minus 2 is R of negative 1, right? But I've defined this in such a way that, R of negative 1 is the same as R of positive 1, right? Because, like, for example, the expected value of x2, x3 is going to be the same thing as x2, x1. Really, the only thing that matters is the difference. And actually, I realized that maybe I misspoke a little bit earlier, which is to say that the right way to say this, way back here when I defined the correlation matrix, is that if everything is real, that I'm really only looking at the absolute value here, right? If I was really being picky, there would be negatives along these diagonals, but I'm assuming that doesn't matter the order here. If I was talking about complex signals, then it's true that life would be a little bit more complicated. So I apologize for not saying that a little bit earlier. But here I have like this, and so on, right? And so if I think about what is the column, what is the system of equations that's going to generate, right? What I don't know are the A1s, or the AIs. So what equation am I generating? Well, I'm going to have R0 times A1, and I'm going to have R1 times A2, dot, 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 all the way out to R of m minus 1 times am. And then what's that going to equal? It's going to equal the constant term, which is basically negative R1, right, if I were to move that guy over. And the same way, I can generate other systems, when L equals 2, I'm going to get a matrix that looks like this. And again, this is going to be like this Toeplitz matrix, right? So it's going to be like R of m minus 2. And there's going to be this structure. And in fact, what I'm generating here is exactly the autocorrelation matrix, right? This goes down to R of m minus 1 again. Okay, so, and on the right-hand side, what I have is going to be the other lags that go from minus 1 to minus m. And so what I get is this system of equations where I can recognize this is just simply the autocorrelation matrix. So I'm going to have, compactly writing this, I'm going to have capital R of the A's equal little r, where this is the autocorrelation matrix, which involves R0 up to R m minus 1. And this is basically, negative of the autocorrelations from, R1 to Rm, right? And so this is a particularly easy thing to do because then all I have to do is take the, R inverse like this, and I get the answer, right? And so in practice then, so how would I figure out, so the assumption is that, initially I'm not told what these autocorrelations are, right? So how would I estimate them? Well, just like we would do it for a real sequence, like suppose I gave you a whole bunch of numbers and I said these numbers all come from the same distribution, how would you estimate the mean? Well, you look at the average, right? And in the same way, my estimate of the autocorrelation lag for time I would be like saying, okay, take over all the data I have, the difference between, those adjacent samples that have that lag, right? For a given realization of data. Right? That's going to be my crude approximation to the expected value. Okay, so this would be how I would get the A's, right? The prediction coefficients that come from the AR process. There's still one more thing to estimate, which is the variance of the noise that drives the process. And so let's return to my equations here. So here, right, I made a point of saying that L was positive. What if L is equal to 0, right? If L is equal to 0, then the left-hand side stuff kind of stays the same, but now I've got something else. So let's just go back to this. So Yule-Walker equation with L equals 0. Basically what that says is I have over here, I'm multiplying it by this. And on the right-hand side, I have the noise and the current thing. So again, if I take the expected value of both sides, what I get is this thing is the same as R0. This is the same as R1. This is the same as Rm. And then what is the expected value of this thing? Well, again, I have to kind of return to how I defined x, right? X was defined as the sum of a bunch of previous x's plus the current value of the noise, right? And so, again, by the same reasoning as before, this v of n is independent of all of these previous values of x, because the only randomness comes from the previous values of the noise, which are not related to this guy. So this is related, this is simply this thing, which is what I defined as the variance of the noise, right? So here I have this thing. And the conclusion is that basically, once I've estimated these guys, right, that writing this in a slightly different way, to get the variance of the noise, sigma v squared, that's just what I get if I sum up these guys, with the assumption that A0 equals 1. And all this stuff is known at this point, right? I've got the R's, I've got the A's, that's how I estimate the sigma. And so kind of the last question is, well, how would I know, what this M should be in the first place, right? How do I know how many parameters in the model I should have? This is kind of related to what I would call detection and estimation theory, right? So how do I know what the right M is? Well, in some sense, this is kind of like fitting a model to data, right? So certainly the more, the more data I see, or the higher that I make this M, the better I can make the data fit the model, right? So clearly things are going to get, better and better fit as I increase M, but in some sense there should be kind of a point of no return, right? So one way I think about this is that, so let's suppose I have all this data from some experiment that I do. And then I let, theta of M be my estimated parameters from Yule-Walker, assuming the model order equals M. So one thing that I can do is I can estimate the fit of the model. This is kind of like a likelihood, right? So it's kind of like a likelihood. As a measure of the probability of seeing all that data given those model parameters, right? So I want this probability to be, high, right? Which means that this log should be also high, right? And so what I want to do is I want to maximize this log likelihood as a function of M. And that kind of tells me, as I optimize over M, make this as big as possible. What I was just saying, though, is that, it seems like it stands to reason that the more parameters I give you, the better I can make the data fit the model. And so in practice, what I do is something more like this. I look for the maximum value over some range of possible model orders, the fit with the data, assuming a model of order M, and then maybe what I do is I, penalize it by this. This is like saying, fit to data, and I penalize larger model orders, right? And you can put a coefficient on here if you want to say how much you care, right? So this is kind of like the idea is that you'd say, okay, there's a trade-off between fitting well to the data and having a really long model, and I can tune this cost function in such a way that I see how it works. And so if you look at Matlab, so Matlab has ways of doing this, of course, and so here's an example of saying, okay, let's suppose that here's an example of making an autoregressive process, right? So these numbers here, this is my A0, this is my A1, this is my A2, and this is like saying filter this noise here, right? This is a long realization of noise. Filter it with, actually, maybe I should make this 2 to the 10th, right? So if I plot y, here is my AR process, right? So you can see that this looks kind of like, you know, spiky, noisy data, okay? And then what I can do is I can now estimate the coefficients that correspond to the AR process. This is like saying, okay, you know, I know that the coefficients I expect are -3/4 and 1/2, and my noise variance should be 0.2 squared, so 0.04. So if I use that, here's what I get from Matlab. So Matlab estimates that, you know, this is pretty close to the coefficients that I put in, right? I expect to get -0.75 and 0.5. I'm a little bit off, and my noise variance is a little bit high. But the longer of a realization I have, the more data that I see, the better that my estimate is, right? So you can see here, now my estimate is really quite good, right? And here I'm using the Yule-Walker equations only to estimate, assuming that there were 2 values, right? 2 AR coefficients. If instead I ask for, say, 10 AR coefficients, so let's go back to a short amount of data, and let's suppose that I hypothesize that there were 10 coefficients instead, now you would see, well, you know, the noise variance is still about right. Here, I get close to the -3/4 and close to the 1/2, and then I have a whole bunch of very small numbers, right? So actually, if you look at the, you know, the sizes of these numbers from 3 to 10 are all pretty small compared to 1 to 2. And so I could look at this and say, well, the evidence is pretty good that I don't need more than 2 coefficients to describe this process. And of course, the longer the process I get, so let's make this again a very long process, if I now estimate 10 coefficients, you can see that now these are reduced by even a more, you know, even another order of magnitude, right? So here I would probably stop and say, well, clearly I don't need to have all this stuff to be able to describe my process really well. So again, this Matlab command is called AR-Yule. And the homework I'm going to give you basically is making you kind of put together those autoregressive processes by yourself. Okay, so that's the end of our first adaptive filtering lecture, and then we're going to get into some deeper things in the next couple lectures related to adaptive filtering.